let's look at this algorithm, stochastic gradient descent with momentum. As input, we have the learning rate schedule, alpha k, which is the same as regular stochastic gradient descent. Then we have the mini batch size m, again, no change here. What we have in addition is a friction schedule, rho of k, and for now we simply assume that this friction schedule is simply a constant. And let's imagine that rho would be 0.9, and this is then in accordance with the standard value we picked for the exponentially moving average in the beginning of this optimization lecture. So the rho might be something completely different when you actually train the neural network, but that's a good way to just think about what happens to have at least one specific example. So no change here, no change here, all the same. We also, again, we sample a mini batch, the same as with stochastic gradient descent, and we also estimate the gradient g at our current position. Let's skip this line for now, and let's go to this last line. And here we see again the weight update, w equals w minus alpha k, and now here we have a v. If you would replace this v with a g, which is the gradient, then we would have stochastic gradient descent. Since we studied this exponentially moving average quite excessively in detail, we can now simply explain what the main change is. Instead of updating the weights using the gradient, we are using an exponentially moving average of the gradient. We are basically using an average of the gradient over the last iterations, and the exponentially moving average is telling us what the weights of the previous gradients are. Therefore, we use this formulation here that makes it clear that this is an exponentially moving average. V equals beta times v plus 1 minus beta times g. This is also called the velocity. So when we start out, the velocity is initialized with 0, and then again, we know this from before, the first time this inner velocity will be set, it will be basically this will be 0, so we'll get 1 minus beta of the gradient. And then after a while, when velocity will be a more meaningful value, so in the beginning it might be too small, then what we will have is that the velocity will typically dominate. So that means that this beta times v will be a more significant contribution to the velocity in the next or in this current iteration than the gradient g. So then, taking one example, that is this ResNet paper where we had the quote from the paper several slides back, then this paper did indeed use beta equals 0.9. And then going back, we also can remember now that that means it's approximately equivalent to averaging the gradient of the last 10 steps. Also, we can see here that we don't employ a correction factor. One simple thing to do instead is that you could start with a higher beta, so maybe you make up some friction schedule, you start with a higher, or that means a lower beta, so let's say beta is 0.5 in the beginning, and then over the first few iterations you gradually increase beta until it's 0.9. Also, one thing that's important to note here is that there are multiple different ways this is formulated in the literature. We're going to go over 3 different formulations. So we're going to look at this formulation first. This is the one that we use in the main algorithm. And here we have the velocity now with a subscript k. This is just a different way to write it, where we make it more explicit that we're at time step k. And so you see vk is beta times vk minus 1 plus 1 minus beta k times the gradient at the current iteration. So in this formulation here, what we're doing is we take the velocity as beta k times vk minus 1, same as before, but now here is a change. We're subtracting out alpha k, this is the learning rate, times the gradient at the current iteration. Now, since we are actually subtracting gradients instead of adding them, this velocity will now point kind of in the opposite direction, not in the, or you know, it's an average of gradients, but the gradients will already be pre-reversed with this type of velocity. Therefore, here in this second step where we do the weight update, we are not subtracting some average, some running mean of the gradients. We are going to add what is already been a negative accumulation of the gradients. In yet another variation here, again we see beta k times vk minus 1. This is the same, but here we simply add the gradient. And then in the weight update step, we subtract minus alpha k times the velocity. The main point here is not to get confused when you see these different methods, because in the end they're equivalent. It's just important to note that you cannot simply copy a beta of someone using one formulation here and use it in another formulation. Therefore, it might also be tricky if people report their own parameters if you don't know exactly what version they are using. So this is one, again, intuitive, aspirational example. Who knows what is really going to happen? But if we have some valley that maybe looks like this, and now we look at the gradient update, then what we could see is that it would always, the optimization would kind of bounce around through this valley. Looking at one such point here, and let's assume that these two arrows show a coordinate system, then we would see that in this forward axis, we have always consistent but small steps, and in this axis going to the side, the gradient is always bouncing around between going in this direction, going this, and so on and so forth. So computing some running mean, this would let us keep this direction here, but this constant bouncing around, these oscillations would be averaged out. So in the ideal case, one could hope that the gradient, the exponentially moving average of the gradient, would look more like this blue line down here. One side note is that there's momentum and also something called Nesterov momentum, and the idea of a regular update is you are at a point here that is in red, and then at this point you estimate the gradient and the velocity. And what you're doing is combining this and then taking an actual step. When looking at this figure, you have to consider that gradient and velocity are already appropriately scaled, that the actual step would be a vector addition. Now in Nesterov momentum, what you're doing is you're taking a step in the direction of the velocity, and then at this new point you're estimating the gradient to make a step. Now it seems superficially that this would require additional difficult evaluations where you would start somewhere, make a velocity step, then maybe you need another forward pass, and then you might need to estimate the gradient. So this is not how this is implemented. It is actually possible to implement this with a change of variables quite nicely without additional effort. Let's now discuss this algorithm, RMSPropo, standing for root mean square propagation. Let's simply discuss this algorithm looking at the update equation. What we can see here from this structure, beta and 1 minus beta, is that again we are computing an exponentially moving average of something. In this case, it's not an exponentially moving average of the gradient, but an exponentially moving average of the gradient values, but squared. Going back to the previous algorithms, they were also computing this exponentially moving average of the gradient one parameter at a time. But what we see here is mainly a notational inconvenience. We not only have the subscripts k to denote the iteration number, we also have superscripts j now. Let's look at the gradient here. What does this mean? So g subscript k is the gradient at the kth iteration, which is the current iteration. And superscript j means that this is the jth component of the gradient. The main reason here is it's not possible to write gradient squared because this is not an operation that traditionally is applied element-wise. Basically, this means that we're doing this exponentially moving average of each parameter j, but squared. Now the update equation itself is also written for each parameter separately. So for each weight in the network separately. So this is the weight at iteration k, and this is the jth weight. And so what we see is that the only difference to gradient descent is this one factor here. If I would take out this component here, it would be the same as stochastic gradient descent, just written for each parameter individually. So we have the new weight is the old weight minus alpha times the gradient. But what we see here is that each component of the gradient is divided by the square root of sjk plus epsilon. What is this plus epsilon? Again, only or mainly for numerical stability. If this value would be 0, then we would be in trouble because we would divide by 0. So since we compute the exponentially moving average of the gradient component squared, we take the square root here to get to something that's more similar to exponentially moving average of the gradient components. Now, the division here has the following effect. If a particular component of the gradient has large absolute values, then we will divide by a larger number here. That means that this has some sort of a dampening effect. Some parameter dimensions where the values are large in absolute value, they will be divided by larger numbers and they will be smaller. And some dimensions where the gradient always happens to be small in absolute value, they will become larger in comparison, because here we will divide by a smaller number. In some sense, this might be intuitive because it somehow helps to make the maybe reduce the outliers, some dimensions that have gradients that are too large, maybe the gradients in these parameter dimensions will be smaller, and some dimensions, some parameters that receive hardly any updates, there the update strength will be magnified. However, this kind of changes the direction of the update. This really changes the direction of the gradient. So it is a bit unclear if this is going to help or if this is going to hurt the optimization. Nevertheless, this has survived as one of the few core algorithms of optimization in deep learning. However, it might not actually be RMSPropo, the algorithm by itself. It is more this one component is reused in the algorithm that might be currently the most popular, which is ADAM. Also, here we can see the algorithm outline, but I think we covered that completely just using the update equations. Now, ADAM is probably the most popular algorithm in deep learning at the moment. The reason it is so popular, I believe, is because it is easy to set up and easy to configure compared to the other methods. One of my colleagues said that ADAM is the second best method for any type of learning problem, meaning that you don't really get the best performance in the end if you had unlimited time to tune hyperparameters, but it very quickly gives you a very good solution that you can live with. Therefore, even in research, people are using ADAM since the models tend to be on the larger side and there is no time to really do excessive hyperparameter tuning since it takes so long to train a single model. The idea is to combine the last two algorithms. We take momentum, that is in the sense of exponential average of the gradients to update the moving direction, and we take RMSPropo, that we have some exponential average over the squared gradients, that means each component is squared individually, to update the learning rate. Let's discuss the update equations. We have two momentum parameters now. That is one, which is beta 1, which is used for the gradient, and beta 2, which is used for the gradient components squared. If we look at this first equation, that is the equation that we used for stochastic gradient descent with momentum. We're keeping track of a velocity v that at time step k, and now we also write it component-wise. So we have velocity at time step k, and it's the jth component, and we have this principle of beta 1 times the last velocity plus 1 minus beta 1 times the gradient at the current time step. So this part here is identical to RMSPropo. This s is a variable that keeps this exponentially moving average of the gradient squared. So it's beta 2 times whatever the old value was, plus 1 minus beta 2, and here again we see the gradient where each component is squared. These next two equations should also look familiar because these are the equations to do the bias correction term that's especially important in the beginning. So the correction term was 1 divided by 1 minus beta to the power of k, so we see the same correction term for both. Of course, each of these correction terms has the appropriate beta in it. One very important part about this correction term is the following. We have this corrected, and it's denoted by a hat. So we have a corrected velocity and a corrected s term, but these are not then used in the recursive equations. So the velocity and the s update equation, they are considering the v and the s without the hat. So this correction can only be applied just for outputting the value. It's not really applied and fed into the recursive equation, otherwise there would be an error. So we use this here basically for updating. And how does this look like? The old network, or the new network weights are the network weights of the last step minus, this is the learning rate, and now we see the velocity from SGD with momentum and the division from RMSPropo. Basically, ADAM is an almost straightforward combination of momentum and RMSPropo. But what are these parameters? Well, so what we see, and that's maybe a typical setting, is that the first parameter, set to 0.9, is responsible for the gradient, and that actually only averages maybe a last few, so we set this equivalent to the last maybe 10 gradients. But beta 2, that is the term responsible for averaging the gradient squared, this is set to 0.999. So this is really averaging, or at least conceptually averaging, a lot of the past gradient squares. Epsilon for numerical robustness can be set to 1e to minus 8, so 10 to the power of minus 8. So this first part, velocity, that's called like, so v is called also first moment, and this is then called the second moment. So again, here is the algorithm written out, but I think it was sufficient to go over the update equations. I also wanted to show 3 other algorithms, and I just call these advanced algorithms because they're not standard. And the reason to show them is more to give you some type of idea what type of papers people try to publish in this area. These algorithms, they might partially, be successful in the sense that more people try them out, but in the end, at least at the moment, people still haven't switched to another algorithm in large numbers. So these type of algorithms are interesting to know from a research point of view. But it's unclear how far it's really recommended to try out these type of new algorithms. One problem is that there might be quite a lot of them, and systematically testing them would be a lot of work. So Rectified ADAM is a paper that tries to improve upon the startup phase of ADAM. This paper came out last summer, and it was pretty popular on several blogs at that point in time. So it claims several advantages, but ultimately what it claims is that it would lead to overall slightly better results. So looking at a general algorithm that can be one of the algorithms we discussed before, mainly ADAM, there are multiple steps. Finally, we have some parameter update, so they use theta instead of w for the network parameters, and they have the step gt gets assigned something. This is the gradient estimate, and then we have the computation of the first and the second moment. There is one computation that computes momentum. This is the gradient, and then we have this calculate the adaptive learning rate. This would be the computation of the gradients, the exponentially moving average of the gradient component squared in ADAM. The authors argue that even though there might be a bias correction term employed, that in the beginning of training there would be a high variance because only a few gradient estimates are influencing these two elements, these two variables, mt and vt. One solution to this problem was warm-up. This is the idea to start training with a much lower learning rate. The authors proposed the following experiment to illustrate the dramatic effect of warm-up. What we see here on top is ADAM without warm-up, and what the authors plot is a histogram of the gradients. So you see like the magnitude here, and then on the y-axis you basically see how many gradient components have a certain magnitude. So what you see is that with this type of starting shape here, the histogram quickly changes, and then it kind of flattens out, and then it slightly or slowly creates some sort of a bump shape again. But here at the end we're already at 70,000 iterations. Zooming in here in the first 100 iterations, what we see is that this histogram is distorted very, very quickly. Within 10 updates, it goes from this type of shape that you see here to this type of what the authors say is an undesirable shape. By contrast, ADAM with warm-up has a distribution of the histogram of the or has a histogram of the gradient component magnitudes that is much more consistent and looks nicer. Also, you notice at the beginning of training there is no strong distortion. So this is the outline of Rectified ADAM, the algorithm where the authors argue you could get even better performance than ADAM with warm-up. Let's identify the major differences to ADAM. We have a gradient update, and then we have the computation of the first and the second moment. This is the same, and we have a bias correction term that is also the same. This bias correction term applies to the first moment. The authors seem to be most concerned with the second moment, the adaptive learning rates. In the paper, they present some sort of analysis where they're concerned with the variance in the beginning of training, and they make two distinctions. So if the variance is tractable, so kind of have to go to the paper for details and analysis, so we'll just say that after a while the variance would be tractable, and then they do something that is quite similar to ADAM. They would do a bias corrected moving second moment, then they have this additional variance rectification term. This is something that they introduce as an additional factor, and then they would update the parameters with adaptive momentum. This would be fairly similar. This is the case that happens after a while, And the main change here is that there's this variance rectification term. Also, the name Rectified ADAM probably comes from this term. But in the beginning, when this is not yet the case, then you will resort to an update step where there's no adaptive learning rate, simply the first momentum and the learning rate. But this, what's computed here with the second moment, this only happens after a while when this is the case. But what exactly are they doing here? What the authors are doing here is they're performing some analysis of the simple moving average, this is the regular moving average, and the exponentially moving average, and they're comparing some computed length. So they compute the maximum length, and then they compute the length of the approximated simply moving average, and then they'll check if that's greater than 4. So the exact analysis, again, you would have to look up in the paper. But this idea should give you some, or this algorithm should give you some idea of the magnitude of the type of changes people try to introduce to modify an algorithm such as ADAM. However, there are probably many such proposed modifications. One thing to note is that this variable really depends on only the parameters beta 2, and this one also here is only beta 2. Therefore, this whole thing only depends on beta 2 and the time step t. This means this is not a data-dependent term where the algorithm would analyze the data. It is something predictive just based on your setting of the parameter beta 2. The authors tell you when to switch from not using this second moment to using the second moment. Lookahead is another paper. This one is actually a very simple modification to existing optimizers, and one way to describe it would be k steps forward, 1 step back. The authors claim advantages as less hyperparameter tuning, fast convergence rate, and better overall results. Lookahead can nicely be explained just using a figure. What we're doing is we have two sets of weights that we maintain, the slow weights and the fast weights. Fast weights refer to what's shown in blue, and the slow weights to what's shown in this color, let's call it purple. Alright, idea is very simple. We start at one particular point, and then we make k steps using the fast weights. And so we'll just make these steps, next step, next step, next step, next step, okay, move. And after k steps, we end up here. And what we do then is we create a linear interpolation between this slow weight point that we started out from and the fast weight point where we ended after k steps. So we end up, let's just say for this, in the middle here. And then we do the same thing starting from here. So this is our new, we could call it anchor point. So we are here, and then we make k steps forward, and then again we average the fast weights and the slow weights, and we are here. This algorithm can be used with almost any optimizer. So, for example, some people recommended to use Lookahead in combination with Rectified ADAM, and they claim that they get really good results on classification problems. Novograd is an algorithm that has the following main idea. It's a first-order stochastic gradient descent-based algorithm which computes second moments per layer instead of per weight as in ADAM. Claimed advantages are robust to the choice of learning rate and weight initialization. It should work well in large batch sizes, and it has a smaller memory footprint than ADAM. Looking at this equation, we can now see that, or this algorithm outline, we can see that there's a loop where the algorithm iterates over each layer in the network. We'll compute a gradient for a particular layer, and then we have a second moment that is computed for a layer. So this second moment, since it is per layer, is actually a scalar value. That means all gradient updates, all weight updates for a particular layer, they are not scaled per weight, they're just scaled all of them together with this one scalar value that couples basically this second moment of all the weights in a layer. That means basically there's less flexibility to adapt the learning rate to each parameter. Is the learning rate correction factor for all parameters in a layer is coupled. If you look at this algorithm outline, you see there's this one term here, which is weight decay that the authors wrote explicitly into the algorithm. But I think apart from that, this is pretty much, the paper can pretty much be summed up by the idea to compute the adaptive learning rate per layer and not per weight. So let's briefly look at this paper that introduces Rectified ADAM, just to give you some idea how this looks like. So here the authors introduced this generic algorithm, and they show several experiments that explain why they believe that this variance is a problem, and show how their algorithm improves upon this by better controlling this variance problem. And then you see some sort of a derivation that justifies the choices made in this algorithm. So that's the algorithm we showed in the slides. And again, there's some more experiments. And all right, let's go to the end. Also, since this is a very simple change, then for a paper, you might want to have more derivations to justify this. So you see some appendix with a few more details. All right. At the end, I would still consider this to be some sort of a heuristic. However, you see for a research paper, it has a pretty nice combination of experiments that explain the problem and also show that the solution helps in practice, at least in some selected examples, and they have a nice explanation what the problem is, and then they have some sort of a derivation that justifies what they're doing is good. And so this seems to be an attractive style to write a research paper like this. One more ingredient that might be even the most important is you need other people to pick up your work and endorse it. There's one researcher that looks at a lot of practical aspects in deep learning, that is Jeremy Howard and his FastAI team, and these guys are extremely strong in practice, and they combined Rectified ADAM with Lookahead and claimed to get pretty good results that are significantly better than what they got before. And so, for example, you see this, how we beat FastAI leaderboard score by blah, blah, blah. So then if you scroll in the blog, then you see, okay, here's what worked. 1, replacing ADAM optimizer with Ranger. this is their optimizer, which is a combination of Rectified ADAM plus Lookahead. And something like this I consider to be a really strong endorsement if there's some independent verification that your idea really works. Since we're already here, we can also look at some of the other ideas that they endorse here. 2. Replacing ReLU with MISH activation function. So as a reminder, we discussed this MISH activation function is a function that looks like this, that actually has this dip. So it is a function that is not strictly monotonic. Also, these are some comments on learning rate schedules. What they're doing is they said they replace one cycle annealing with flat plus cosine annealing. So this was their previous idea where the learning rate starts out small and then it increases. This was probably the idea to compensate for this necessary warm-up, or to include this necessary warm-up with ADAM, and then there was a decrease in the learning rate. Now, what they endorse is to start out flat and then have a cosine annealing to reduce the learning rate. And again, they mention these effects, how the different parts of the network are coupled together. So they said that using these new optimizers that they tried, which is Ranger, the combination of Rectified ADAM and Lookahead, that this wouldn't do so well with the previous learning rate, but this would do better with this learning rate. Fourth, they found some problem with resizing, where they were first resizing images to 160 pixels and then from 160 pixels to 128 pixels. I don't really know why they had this type of step, but then they found out that resizing from the original size down to 128 pixels was giving a significant boost. Fifth, they added a self-attention layer. Self-attention layers are something we haven't discussed so far, but we will introduce them later on in this course. Alright, this concludes the discussion of optimization, and just a reminder, it is important, besides reading several of these research papers, to also look at blogs from some of the leaders in practical deep learning, and very often good ideas are also discussed by people just posting on social media or on blogs that report on their experience with research papers, and these type of blogs can often help you to get settings and better ideas for fine-tuning a method where people report, okay, maybe if we use this learning rate schedule or we change the parameter settings